I wonder if I should talk.
Talk like this.
Has everyone sort of gotten their food? I guess it's good to get started. Today we'd like to welcome Professor Stefan Hoderlein, who is at the Kennedy School, and some of you may have noticed I referred to him as being at Harvard Econ when I sent out the reminder emails, and in my defense, he was at Harvard Econ earlier this year, and has actually been at a number of illustrious schools around the country, Caltech, Brown, Boston College, and so his work has been influenced by, I think, a lot of exciting research going on in these different places. And Professor Hoderlein obtained his PhD from a joint program between the London School of Economics and Bonn University. And his research is mostly focused on modeling heterogeneity, and we're really lucky today to have an exciting example of that for consumer demand and welfare estimation. So without further ado, I'll let you take it away.
Oh, perfect introduction. Thank you so much for the invitation and the opportunity to speak here. I'm absolutely delighted about that. I should actually excuse myself almost because I will be at the Kennedy School starting January, and I anticipate also to be here. It's a little bit of an overlap because their Kennedy seminar is also on Wednesday, but so I'm here talking now, and then maybe or probably you will meet me later again, but I'm looking forward to that. So today I'm going to talk about something which is genuinely economic, yet the model is still somewhat related to the treatment effect and evaluation type models that also have been studied here a lot. What I want to do is essentially recover from the data a distribution of an economically relevant parameter, and that is in a heterogeneous population, that is the welfare effect. So there's a nice sentence that a pretty famous economist once coined years ago, 30 years, and I actually kind of described it pretty good. So we want to invert the distribution of the data to obtain the distribution actually of, in our case, not beliefs, but preference-related parameters. Okay, and the specific application will come from a gasoline and a counterfactual experiment of introducing a gasoline tax of 5%. So that's going to be the welfare relevant variation that we're looking at. And the key innovation here vis-a-vis to the literature in economics is that we allow for extensive unobserved heterogeneity. So there are observables in our model, and we will control for everything that we can control by observables. But there's now a pretty common or pretty widespread belief in economics that even after controlling for all kinds of observables, there are many things that are economically relevant, preferences, that we don't observe and that have a huge influence. Okay, so think of you as, in my data set, a lot of you would look observationally equivalent. Let's say between late 20s and mid 30s, roundabout. I'm also not mid-30s, but anyway, in that bracket, male, female, but there may be wild differences between you that I just cannot observe. Okay, and in our case, of course, we're specifically interested. Think of a government wanting to impose a green tax, and trying to assess the effects of that, and we're interested in the distribution of the effects. So actually, we're estimating a density. We show that we can first point identify and then estimate a density of these welfare effects. So the approach that we take thereby is going to be non-parametric, and it has a bit of a structure that's typical for econometrics these days. So in that sense, I'm kind of a run-of-the-mill kind of guy. Okay, we'll first show non-parametric identification. So we'll first show that in an ideal infinite data set, if I had the population variables to my disposal, I could identify the object that I'm interested in, and then we will imitate the identification principle. This is called the sample counterparts estimate. You probably may all know that, I don't know. But we, in economics at least, econometrics, it's called sample counterpart estimator. I'm not going to talk too much about the asymptotic properties of that, but you know, this is based on several papers, so you can find that in my work. And a particular focus of that as a building block is going to be, in a first stage, the estimation of a demand model with random coefficients. And to give you an idea what we're talking about, you know, this is not the application. Later will look a little bit different, but this is essentially also the application. What you see here is a mountain, okay? So these are lines of similar altitude, okay? You know, I come from southern Germany, close to the Alps, so think of that as the Matterhorn, okay? You know, kind of a steep mountain here. Here's the peak, obviously, okay? And this thing represents the two-dimensional densities of income and own price elasticity of food consumption. Okay, so a point, let's say here, for instance, represents an individual with an own price elasticity for food of -1 and an income elasticity of 1/2. For those of you who have never heard elasticity before, that's something we like to use. So this tells you how many percent your food consumption changes if income changes by 1%. And you see most of the mountain is actually fairly well contained, you know, by that set of lines here. So the vast majority of the population, so to speak, you know, this is your density here, as again, like a Matterhorn, okay? You know, most of your population has income elasticities that are below 1 but higher than 0. So if income increases, they consume more food, but they underproportionally consume more food. Makes a lot of sense for us, okay, because food, I mean, there's only so much you can eat. And then the price elasticity is kind of all over the place. There's a part of the population who doesn't respond to price changes in the food, and then there's a part of the population that does respond to price changes in food. So this kind of object is a key building block, and I will tell you for a good part of the talk, time permitting, how to identify and estimate this object, and then I will go on and tell you what you can learn from this object about the welfare effects that we're kind of actually interested in. Hey, long time no see. Okay, good. So there are some references. With that, basically, I mean, you're not really economists mostly, so this is kind of the classical literature. Then people have applied non-parametric regression techniques, which always assume that implicitly always assume that the populations were homogeneous. And then there's another literature that actually in economics or in econometrics kind of started with our paper here. Some of you may know Enno Mammen, who's a pretty famous stats person in Germany. Anyway, so we started with that paper, but there was a predecessor literature in the Annals of Stats about these types of models. We kind of we built on that and made them econometric, okay? And meanwhile, there's a pretty active literature on that. And then there's work, kind of applied work on gasoline demand. There's actually quite a bit of applied work. Okay, that's the literature. And the talk today, again, time permitting, 1 o'clock, right? A little before. Oh, okay, good. So we actually don't have to rush. That's good. Okay, so I'm going to finish earlier. Don't worry. Okay, so I'm a good guest. But at least I don't have to rush. Okay, so first I'm talking a little bit about the economic background, like what is a welfare effect, okay? Then I will introduce that building block, the random coefficients demand model. Then, you know, I will tell you how you can come from that random coefficients demand model to the distribution of welfare effects. And then we're going to apply that and see, you know, to our 5% gasoline hike, you know, green tax. And then time permitting, I'm also tell you that the future is glorious and golden in that literature. Hi. Okay, so the economic background. You know, this is actually nowadays pretty much textbook. So for those of you who have ever taken basic microeconomic PhD kind of class, Mascolell, it's all in Mascolell. maybe some of it even as exercises, okay? But it's really built on work of Jerry Hausman at MIT in the 80s and 90s. So to introduce the notation, we have a dependent variable which is continuous, y, okay? In our case, gasoline. Then we have an outside good. That's more for economists, okay? So we separate gasoline consumption from everything else, okay? And to be able to do that, we have to invoke an economic assumption, which is called separability of preferences. So in this paper, we're focusing on gasoline in isolation until the very end, at least, okay? And if you do that, then you have to work with something which is called a numeraire good, which is everything else. That doesn't really play a major role here, okay? And then gasoline is a function, under this assumption, is a function of its own price and income for every single individual, okay? All of these variables are continuous, so that makes the whole setup different from, you know, treatment effect approaches that are studied here and elsewhere. You know, Alberto does a lot of work on that, and I guess Guido did a lot of work on that. Well, still does, but not here. Okay, so in our world, everything is continuous, and the object that we can estimate for every individual, at least in principle, okay, is the Marshallian demand function. So it relates gasoline consumption to its price and income. And then the welfare measure is the so-called compensating variation. So this is what we can measure with some hand waving, okay. This is the object that we're after, which is, you know, which we can relate in a second, okay. So this is the welfare effect. It's varying the price from some base price for a given level of utility to some, let's call it target price, okay. And then how are the two related? The thing that I can observe and the object that I'm interested, they're related via a set of differential equations, okay, and they take this form. So the welfare effect lambda of P would really be the solution of these differential equations. Looks somewhat nasty, but the nice thing is that there's this Hausman work from 81 that says if the model is linear for an individual, okay, then this differential equation has an explicit solution and had that kind of slightly nasty form. Forget about the formula, okay? We don't really work a lot with the formula, but it has a form that relates the welfare effect to, you know, prices, income, and the parameters here. Okay, so there's an explicit solution in this special case. Okay, that's for one individual. What is the relationship to data? Well, we're going to assume that we have a single cross-section, okay? We don't have a panel or something. We don't observe individuals repeatedly. We have a single cross-section, but everybody in that cross-section is characterized by a linear model, okay? So the maintained assumption is that everybody's gasoline demand is linear in these parameters. You know, this could be log prices and so on, like in OLS, okay? But in parameters, this is linear. But now the key innovation is that these parameters themselves vary across the population. And that's why I have denoted them by capital letters. Okay, so we all have a linear demand model for gasoline, but you may have a beta 1 that's pretty close to 0, and he may have a beta 1 which is pretty close to, you know, if you think of the elasticity results that we had before, -2, and I have one somewhere in between, okay? So we all share this commonality, but our parameters vary in a continuous fashion across us all here, okay? And actually, I mean, just as a little footnote, if P were binary, which in our case it's not, okay, then actually a representation like this would also always hold for the treatment effect model. So in a heterogeneous effects treatment effects model, where the treatment has heterogeneous effects. So it's a little bit like treatment effects, but once you add continuity of prices, the linearity is a structural assumption. So linearity is our structural assumption, but we want to be non-parametric about the distribution of the betas. Okay, so we really want to get in the end, at least at an intermediate stage, we really want to get the Matterhorn. Okay, so we want to be non-parametric about that. Okay, so ultimately, of course, we want to use the Matterhorn to get the density of these welfare effects using this formula. But the first stage is we have to first get the Matterhorn and then use that relationship between Matterhorn and the other thing that we're interested in to get the distribution of welfare effects. So how do we get the Matterhorn? Okay, and what we do here is as I said, I mean, this is fairly econometric in that sense. We first establish identification, and we establish identification non-parametrically. So the only assumption that we maintain is linearity of the model, but we show that whatever the distribution of beta is, under an independence assumption, it's always identified. Okay, so in that sense, we show robust identification as a thought experiment. Okay, you know, we assume some kind of smoothness here on the density, but nothing substantial. So the density of random coefficients is not normal or logistic or anything else. Okay. And what we will show in this, in the underlying papers, I guess, is that f beta is non-parametrically point identified under an independence assumption. Once we have established non-parametric identification, there are two ways to proceed. One of them is assume that f beta has some parametric form, like for instance jointly normal. What I'm going to do in this paper is I will actually directly construct a sample counterparts estimator using the insights that I have gained from the identification exercise. So essentially what you can think of that as replacing the population distribution of the data with a kernel estimator with some hand waving. Okay. All of that, as I said before, depends crucially on the independence conditions, or whether the b's and the x's are correlated or not. So for most of the talk, I'm going to assume that they're uncorrelated. They're actually fully independent. Okay. And then later, I will talk a little bit, time permitting, about what happens if there is correlation, which in economics, we always believe that there is correlation. Okay, so that's maybe another trait of econometrics or economics. Okay, so let's talk about the Matterhorn. So this is our model in a stylized form. Okay, so I've now taken prices, income, and the constant to be the x vector, and this is our vector of random coefficients, and we assume full independence. Okay, and then the goal is, with just that minimal structure, to identify and estimate f beta. Okay, to do that, it turns out, and now it starts to become a little bit ugly, but I spare you 99% of the really ugly details, okay, to put all variables on the unit sphere, just normalizing by the norm. Okay, so that means if x is a vector, that means the constant, the first variable s1 is constant divided by the norm of x. The second one is x1 divided by the norm of x, and so on and so forth. And we do the same thing with a dependent variable y, and then, you know, what we have instead of the distribution of y given x, we have the distribution of u given s. But that model here still continues to hold if I divide both sides by the norm of x. Okay. Okay. This is the key tool now, the Radon transform. The Radon transform is the integral of a function over a lower dimensional hyperplane. This is the formal definition. So it has an angle. You know, we're working on the unit sphere. Okay. And it has a distance from the origin. So the variables are supported on the unit sphere, but then y has a certain, you know, it's either long or short. And the Radon transform is then, you know, exactly of a function g, okay, is exactly the integral over these type of hyperplanes. And why is that a useful concept? Well, in our model, with the independence assumption, you can actually show that the distribution of the data is the Radon transform applied to the density of random coefficients. So we are this is an integral equation, so we're entering the realms of functional analysis. Something very useful for those of you who have never entered the realm is think of this as a vector and this as a matrix. It's actually pretty much what it is, just infinite dimensional. Okay, so this is like pre-multiplying a vector by a matrix. And what we really want to do as an identification principle, we want to invert this matrix, like multiply with R minus on both sides. Okay, so non-parametric identification is actually showing that f beta can be written as R minus applied to the density of random coefficients. And because of that underlying Radon theory, we know that there's a unique inverse and that this is uniquely possible. Let me explain for a moment what this does actually, because I think that's cute. So actually the original paper, where did I put the black marker? I know that the black, oh here, okay. So the original paper actually had a third co-author other than me and Mamen. And the third guy was actually somebody giving a talk on computer tomography at our department until we kind of figured out that computer tomography and economics have actually a lot of things to get to, are actually related. So what do people do in computer tomography? So God forbid you may have problems with your brain at some point, okay? In this case, they would put you into a tube, okay? And then this would be a kind of cross-section of, this is, I cut now the tube somewhere in the middle, and this is like cutting through your head. Okay, so this is your head in the tube. Okay, and what they do then is in deterministic steps, they actually send a ray through your brain and measure the time that it takes the ray to penetrate your head, actually, not just the brain. Okay, so let's suppose this is 0.4 seconds, okay? Probably much shorter, but just suppose, okay? So along this angle, there's more mass, okay? So there's more brain, so let's suppose this is 0.5. Let's suppose along this ray, it's 0.25, and so on. So for every one of these angles, I get a number. And the number, if you think again of our Matterhorn, depends upon how much mass I have integrated along this ray, okay? So think of these as the hyperplanes and the mass that I'm integrating over, okay, like our mass, our density of random coefficients, the brain density, as determining this number. So this number is really the integral of this higher dimensional object over this ray, okay? And our minus is determining from these numbers and the angle that we have, okay, the original mass, okay? So kind of given these numbers, and I know that they're, the result of sending this ray at certain angles, okay, how can I get back to the image of the brain, okay? So this is what the Radon transform and the Radon inversion does, and fortunately or funny enough, our random coefficients economic model has the same structure with one subtle difference, and that is, this would be our x's. In computer tomography, you're like an experimenter. You can kind of do that deterministically. In economics, the x's are, price, income, whatever, come from some other source. Okay, so we're not going to have deterministic variation here on the sphere. We're going to have densities. There may be more here, and less here, or something like that.
So it depends upon the independence assumption.
Exactly. Absolutely. It completely uses. Absolutely.
So another example of this is ecological inference.
Oh, okay.
Making inferences about individuals from agriculture. It's exactly the same.
Oh. Very good. I should look at. Actually, funny enough, because there's some work in economics on ecological inference too. I actually, at some point years ago, looked at that, but I never saw that. Yeah. Thanks for.
2 pages in my book that explains what a PET scan is.
Oh, okay.
I'm always afraid that
Very.
somebody who knows what a PET scan is going to be.
Very cool. Very cool. Very cool. I will have to look it up. That's very interesting. I never saw that. Thanks. Okay. So this is R minus in principle, and you see, what this says is that in some abstract way, we can go from the numbers and the angle to the brain and back and forth, or in our case, from the data to the distribution of random coefficients. Now the problem is, this is an operator, so it's like an infinite dimensional matrix. You think that, let's suppose that this operator was compact. I'm not even sure actually it is. But most often operators are compact, then you can have this eigenvalue decomposition. And what this means is actually you would have a decaying sequence of eigenvalues, and infinitely many of these eigenvalues would be infinitely close to 0. Okay, so what you're doing here is you're dividing by 0. Okay, I mean, you're dividing actually by near 0. And in the population, that's not a problem because in population land, you have infinitely many observations, but this is something that you cannot use one-to-one to construct an estimator. So instead, what you have to do is you have to introduce a tiny artificial bias that you control yourself. And this is this little h here. It's like a bandwidth, a non-parametric kernel density estimation or something. And you control that bias, and you let that bias, or actually rather the parameter which causes the bias, tend to 0, like a bandwidth. Okay, so actually the asymptotic will be a little bit like kernel density asymptotics, like from the flavor. Okay, and then you can show for a properly defined regularized inverse that if you really let h tend to 0, you can still get, an r minus in the sense that if I project the vector with r and then apply the regularized inverse to it in the limes, I'm recovering f beta. And this regularized version I can then use to construct a sample counterparts estimator. And what is the idea of this regularization? I'm not sure how many of you have ever seen ridge regression. I have a quick, one person. Oh, okay, many? Okay, very good. So then I don't have, so if x transpose x, same thing. If x transpose x is near singular, has an eigenvalue close to 0, what you're doing is you're adding something like h times the identity to push the eigenvalue away from 0. This is what this does, okay? And you can think of this here as doing the exact same thing. The problem is that our matrix, our x transpose x, is generically close to 0. Okay, so you have to do ridge regression. Okay, but it's the same kind of intuition. You want to get this eigenvalue away from 0. Okay, and then this is what it is. Okay, so this follows from the Radon theory and the way that we construct the regularized inverse, and then the sample counterpart estimator. This is just a formula. I actually show it in a second. Okay, and this one is going to be the sample counterpart. So we're replacing, it's going to be a little bit difficult to see in a second, but what we're really doing is we're replacing the distribution of the data by a non-parametric estimate, and that will allow us, this is a theoretical principle, if you like, that recovers f beta, and this will give us a sample counterpart, an imitation of that theoretical principle, and will give us our estimator for f beta.
So Stefan, do you need any regularity conditions on the density? I mean,
on the density of the random coefficient, so that the asymptotic behavior, like in kernel density estimation, will depend on the smoothness class. So there's like to describe the asymptotic behavior, there are some general kind of Sobolev notions of differentiability, essentially differentiability. Okay, so like in kernel density estimation, we will assume that this guy here, this guy is so and so often differentiable. Okay, so this is the, but we're not going to assume, just to repeat that, anything like, this is normal or something. Okay, and if you look more closely at the formula, the operator, the regularized operator, or actually I should say the inverse of the regularized inverse operator, that's the right way, has a kernel, okay, and after some rearranging I can represent my random coefficients density estimator like that. And for those of you who have ever seen kernel density estimation, this is awfully like kernel density estimation if it weren't for this guy here. I mean, not awfully, but this one is same structure as kernel density estimation. then we still have to divide. These are the transformed x's here. Okay, so we have to divide by the density of the transformed x's, but it's a very similar type of structure. Unfortunately, the kernel is not the kind of kernels that you know. Actually, the kernel localizes in the inverse, in the other space, so to speak. So it regularizes in Fourier domain, or actually in frequencies. Okay. So what you get, these are just examples for what they look like as a function of the bandwidth, and I think this is the dimension, and I think R here was actually the differentiability, if I'm not totally wrong. So there are functions like these, okay? That actually has a little bit of an implication. Since we have time, I actually like to speak about that. So in regular kernel density estimation, if you over-smooth or under-smooth, like let's suppose this is like the true density. If you over-smooth, you get something like this. And if you under-smooth, you're going to get something like that. And ideally, whatever procedure you have to pick the bandwidth, we actually have no procedure to pick the bandwidth, just to be clear. Okay. But I guess one could. I never thought about it too hard. Anyway, so whatever procedure will hopefully spit out the right bandwidth so that you get this optimally smooth thing. So the interesting thing is, because you're localizing in the other domain, you're localizing in this domain, but you're using data in the, always think of the Radon transform in this other space. What happens here is that the regularization is in these frequencies. So these guys, they will gonna have some outlying hills. So what will happen to the Matterhorn is it will look like Chinese mountains. Do you know these? I mean, there's this wonderful, mountain range in China where, you have some trees and then always have mist here. That's what's going to look like. So these things here, they will grow, okay? And you can actually see a little bit here that they are in some kind of frequencies, okay? So unfortunately, because the localization is in that other space, you have to be, picking bandwidth is really a super tricky thing here, and it's not gonna result in something which is mildly similar to this one, but rather it's going to result in these kind of going from the Matterhorn to the, I should know the mountain range. I don't, but probably there's somebody Chinese here who can help me. Well, to that kind of mountain range, okay. Okay, so that's just as an aside, okay? So anyway, so this is, in our application, this is going to be our consumer demand model. Now, what do we learn from the econometric analysis at large? This is a super weakly identified problem, okay? So it's very akin to deconvolution in some ways, okay? It's very hard to learn from the data about the object of interest. So I had the sentence initially, we want to invert the distribution of the data for the object of interest. It's very hard to do that here, okay? So the process of learning from the data is very hard. There's there's a very strong curse of dimensionality, meaning that even in the best possible scenario, depending on, the asymptotics actually depend on the decay rate of the densities in the tails, to answer a little bit your question. So even in the best weather kind of scenarios here, we get twice the curse of dimensionality. So usual kernel density estimators have something like, the rates are something like that, okay? And what we're going to get here is we get a 2D, okay? And that's even in the best cases. In the worst cases, like in deconvolution, you can get log rates and stuff, so don't even go there. But and intuitively, why does that happen? Well, there's one curse of dimensionality that we incur here, and then there's another curse of dimensionality that we will incur when we invert, the distribution of the data for the thing that we're interested in, okay? So the quick upshot is, as an applied person, like, what do we learn from this, okay? don't do it with more than 2 or 3 dimensions. Like if you don't do non-parametric regression with more than 5 dimensions, you shouldn't do that with more than 2 or 3. I mean, you cannot visualize it anyway, but you could visualize the marginals, I guess. That also has an interesting implication, both things together, for the parametric literature. There's Ariel Pekis is actually also, sitting not too far from here. So there's a literature in economics called empirical I/O, and so the P is Pekis here in this model, and he will win the Nobel Prize for that model at some point. Okay. Now, what they always find is they find what they call numerical instability. So they assume a more complicated but parametric version of a similar model. And the implication of the theory exercise is actually, no, these are not numerical instabilities. These are fundamental difficulties to learn, from the data about the object that you're interested in. So actually, this kind of insight here that we can gather from these models is like far-reaching because it allows us to understand some of the, to be honest, crappy behavior that we get when we apply these models to data. Okay, so we have to be cautious, not too many dimensions, and we can expect there to be difficulties. And also this issue that the bandwidth selection is a little bit harder is also related to the same thing. Okay, so that was the Matterhorn, and will give us the demand model that we're resting on. Okay? But we wanted to have welfare, okay? We wanted to have our 5% gasoline price change. And how do we get from the demand model to welfare? Well, we maintain the same independence assumption. And then you can actually show by some nasty but not fundamentally difficult calculations that the distribution of the welfare effects is some functional of the distribution of the x's, now kind of not transformed here, okay, and the distribution of b. Okay, it's just a formula, okay. I wouldn't be able to compute it, but fortunately a computer can. Okay, so just a formula. And then we can construct an estimator by, again, just plugging in our Matterhorn estimate, plugging in, let's say, a kernel density estimator, and evaluating that integral will give us our density of welfare effects. Okay, so it's kind of a derived quantity here, where we made use of the economic structure. And then there's a distribution result, so to speak. For every value of lambda, we can describe the asymptotic behavior. And kind of the cool thing here is, I told you before, don't do random coefficients with too many dimensions. Since we're integrating out most of the dimensions, the welfare effect actually, quite astoundingly, have the same behavior like a non-parametric one-dimensional density estimator. In particular, they have the same rate. So this is the univariate non-parametric rate. So we can hope to be able to identify that guy, to estimate that guy, like reasonably well with the data that we have. And we don't really use the variance, we use bootstrap, but anyway, there's also a variance formula. So univariate non-parametric rate kind of makes sense. And we don't really show that the bootstrap actually does work, we just have some mumbling somewhere, okay. Okay, so that's all the theory for today. Let's chat about the results. So what we're using here is the 2001 US National Transportation Survey. We exclude some things like diesel cars or electric cars. I'm not sure in 2001 there were too many electric cars. Maybe not, but anyway, we exclude them. Okay, and then the households, you should think of those as being randomly sampled across the entire US. That's actually important when we talk about endogeneity, since I'm not talking about endogeneity. Maybe it does matter a little less. And then the key variables here that we use is the annual gasoline consumption in quantities, okay, in gallons. And we do that by dividing the total miles. So we know what the household, how many miles the household has actually driven in any given year, and actually 2001. And then we divide it by an estimate of the gas mileage, okay? And that estimate is actually a function of, so it's an imputed thing, so this is going to be measurement error ridden, and we don't really have a good way to deal with measurement error here. I should say that. But in any case, you know, this is obtained from like tables in the, you know, AAA, American Automotive Association, where they say, oh, you have a Honda Accord, you know, you get, I don't know what, 25 miles per gallon or 30 miles per gallon or something like that. Okay, and then we also have the price of gasoline kind of get by a similar, you know, we know how much they paid actually, and then we can get the price that they have paid on average in every month, okay, from that. And then there are a bunch of household characteristics, and just to be clear, we're going to control for household characteristics. So whatever heterogeneity I show you later is heterogeneity where I have, and we can talk about that a little bit later in a somewhat debatable way, but anyway, controlled for some demographic variation. Okay, that's a table of the summary stats here. So the mean household in 2001 had a yearly gasoline demand of 1,200 gallons. Okay, how many gallons do you, well, I mean, this is in 2001 where the cars were probably less efficient. Seems now that I think about it, seems a little bit large to me, anyway, but that's what the data show. Okay. And here you have the distribution, so you see there are actually people who have 90% individual has like twice as much, and the 10% individual has 1/6 of that consumption. So there's a lot of variation in gasoline demand. And you know, these were the glory days. Okay, the price per gallon 133. You know, that's 2001. You know, it's not even like 1981. Especially for me as European, that's a ridiculous price. But so I think that price should be higher. So let's not talk about politics. So the annual household income, this is household, not individual, okay. The mean is around about 50K, makes sense. The households have close to 2 drivers in the household, and there are a bunch of kids on average, okay. Yeah, and then there are some other. So what we're also going to have is whether people are in rural areas or urbanized areas or in New York City, okay. But in addition to that, we also have a measure of the population density. So we will control for both things, you know. I mean, obviously how much you drive depends on whether you live in the middle of the woods or not. Okay, so let's first do kind of standard, what, you know, people have done, I guess, with that data 1,000 times. Standard regressions. This is the income. These are elasticities, actually. We're later going to do levels, but this is just to inform you, okay? So the income elasticities is if income goes up by 1%, then the gasoline consumption goes up by 0.3%. And if the price goes up by 1%, then it goes down by 0.5%. And the interesting thing is, as I said, maybe I can talk about it a little bit later, but especially the price coefficient is actually somewhat responsive to correction for endogeneity. And that's pretty much in line with the literature. Okay? So our data give us the results that, you know, you would kind of expect. Now let's do the random coefficient. So this is our model now, and this is what I said before when I said, you know, the correction here is somewhat whatever you know. So we've thrown the correction, the demographics here in with like an additive parametric term. Okay, there are other ways to do that. So for instance, the random coefficients, if we're really interested in specific types of demographics, let's say we're interested in whether the welfare effects for women are different than welfare effects for men, or black and white, or whatever, pick your favorite thing. We could let these coefficients also depend on observables, okay? So we're not going to do this today, but if you're really interested in some of that, you could. It's compatible with a framework. So you could this could be partially random and partially determined by observables.
But that helps you deal with the independence assumption, so that seems important.
Absolutely. No. You're absolutely right. I mean, controlling for household observables, so that was a very good point. So controlling for, what we really do here later is then we assume that beta is independent of X conditional on Z, which means that, of course, people in the countryside, they have a preference for driving because they are in the countryside, but once I condition on countryside, okay, things like income and the preference for driving are independent. Okay, so unconditionally there may be not, and that's, I guess, exactly what you're saying, right? So this is not just having as additional regressions that I'm controlling for. This is also, as to be totally correct, I should have added that to motivate the independence condition better. This is like selection on observables. Or controlling for observables. What's the proper name? It kind of varies from literature to literature, but if I condition on the propensity score, something like that. Okay, in the treatment effect literature, of the observables, I guess. Okay, and then intuitively what we do is we're going to partial out that part, and we want to get the joint here of these guys, and then we want to use, this is the Matterhorn, okay, again, we're going to use the Matterhorn and the data to get the distribution of welfare effects.
So Stefan, because of the weakly identified parameters, does it matter the support of the
excellent question. Yep, absolutely. Do you want to know all the ugly details here, or is that okay? Good. So, for a long time, and that's actually still ongoing research. So for a long time, these models were only studied under a full support assumption, which if you log variables in these variables at least is not that bad, but potentially could be. So actually now started a project, and I think we have solved the biggest problems, but there's no paper yet, where we show what happens if you have bounded support. So this is a little bit like as if I wouldn't rotate my rays on the entire sphere. So if I would just pick, my data were just such that I could only get this guy here. So it turns out if you make the appropriate assumptions about the brain, and you actually you have to assume much less than you would expect, okay? You can actually kind of complete the picture from just observing that part. And, that's actually, it's not obvious if you draw it like that, but it's actually kind of related to, so for instance, analyticity. Can I cut this out later on? That actually does the job. So if you can kind of continue the if you know a distribution on a certain interval, and if you can kind of continue that, that's what you have to do. And for instance, if you know that on the interval, the distribution is something like a 200th order polynomial, in theory you could estimate it, and then you could complete that. Okay? So you can do stuff, but you have to invoke additional assumptions. And that's very important. So one interesting question for economists, of course, is then also not just what happens if the x's have bounded support, but also what when you know that the random coefficients have a sign, right? So for instance, for the price effect, we may assume, although we'll see in a second that that's not that clear cut, but you may assume that everybody reacts negatively to a price increase. So if you have that could kind of offset a little bit the limited support, but we still have to work on that. So that's still ongoing research, but a very good question. We can actually even do with countably discrete, funny enough. Okay, so anyway, so this is now the Matterhorn, okay, for the gasoline. This is the gasoline Matterhorn, okay, and what is this? On the x-axis, we get the own price effect of gasoline consumption. And that is if gasoline increases 1 cent, then yearly gasoline consumption decreases by 2, 4, 6, 8, 10 units. Okay, so this is this axis. And the income effect is if, I think this is a K, so if income increases by $1,000, then gasoline increases by 5, 10, 50, and so on gallons. Okay, so everything in the plane is kind of measured in gallons, and the units to which this responds here are pence. Okay, and here it is 1K US dollars. So it's not logs. So your remark is pretty important actually. So if we do it like that, then you see this here is the OLS point estimate. So if you just did OLS with the same data, you would get one coefficient for the entire population, and this would say, okay, you know, the representative agent decreases his or her gasoline consumption by 5 gallons with a 1 pence price change and increases it by 8 gallons with an income effect. So you see the peak of that mountain is round about where the OLS estimate is. So, oof, okay, so we're not getting crazy results, okay? And what you also see, the whole thing is a little bit, that's maybe a bad graph, but the whole thing is a little bit skewed here, okay? And another interesting thing from an economic perspective is that you either have people who are not reactive in any dimension, or they are actually pretty reactive in both dimensions, but you don't get people who only respond to income changes and not to price changes and vice versa. Okay, so either they don't react or they do react, and then they also react in the directions that, you know, if prices go up, consumption goes down. If income increases, consumption goes up. You know, things that make sense. So the results are sensible in as far as the conditional, I should really say, independence condition holds. So, even with exogeneity conditional on observables, we get what I would say are plausible results. Not by construction, no.
Well, I mean, but it's making sort of the same assumptions.
Yeah, well, if the model is correctly specified, I guess. Not exactly, but well, that's a very good thing. Yeah, and that's a very good point. I never checked this, whether you can mathematically show that it would lead to the exact same thing or not. Because I didn't assume anything about symmetry of the betas. So the betas could be skewed.
It's the independence assumption. In ecological inference, we have the huge disadvantage of sometimes actually knowing the truth.
Seems not like it, isn't it?
And so then the estimate, I mean, sometimes it's just like nowhere near there.
Yeah.
And then if the only assumption you have for that particular data set is independence, that's the problem.
Yes.
To see it really clearly.
Yeah.
You can assume, just like I assume like here, like you don't have to assume independence. You could assume
Something else.
Even if you didn't have other covariates, you could assume some type of correlation, and then that shape is going to change in a big way.
Yes, but to be honest, I mean, yes, but to not oversell our methods, once we were to allow for correlation, we would have to come up with a mechanism for that. So this is non-parametric analysis.
Why would you have to come up with a mechanism?
So this is a non-parametric analysis, and we don't just have a correlation parameter here or something like that we could leave free. Okay, so this is not that this is maximum likelihood, and if you have a correlation parameter, then you just have another parameter to estimate. This is really a one-to-one mapping from the distribution of the data to the distribution of random coefficients, and there's no additional.
That's in that transform.
Yes, but the transform Radon.
The Radon transform.
Yes.
But that Radon transform assuming independence.
Exactly. But if I assume something else, yeah. Yeah, exactly. So then I don't even know. I'm not even sure that's one. Yeah, exactly. And then I would have to probably, I mean, to be honest with you, then I would probably have to specify exactly what I assume, not just up to a parameter that I then estimate or something, like a correlation, but literally the exact other transform. Like, maybe it's possible with a copula or something like that
I have no idea how to do it.
Yeah, I know.
But the fact that it's hard doesn't mean that that's the way the world works.
I know, that's a very good point.
So not fair.
Well, I mean, let's put it like this. We have to start somewhere, and exogeneity seems like a good starting point. But I agree. I mean, the good thing, like for economists, and I can actually, well, I'm starting to get a little bit on time pressure, but I can talk a little bit towards the end. We also like IVs a lot, like specifying how the endogeneity arises from truly exogenous sources of variation. And actually, I show that in a second, you can integrate IV here into that framework.
So empirically, it seems like a situation where you could actually, assume like a bivariate mode distribution for the data parameter.
Yeah, maybe.
And then you get the same kind of
maybe. But my personal guess would be if you did, we could actually specification test here. We could have a maximum likelihood estimate, let's say, of the normal distribution, and then test a non-parametric estimate versus a parametric alternative, or a parametric model versus a non-parametric alternative. And most of the time, a test would reject. Okay, so even if the thing is slightly non-normal, if it's integrating over the betas, but you're absolutely right. I mean, we could do stuff here, which we don't. Okay.
And how did you pick the bandwidth?
Well, I picked the bandwidth. You guys are not listening here. Okay. There's some food left. I picked the bandwidth such that the results made sense to me because of the Chinese mountain. Because of the Chinese mountain effect, if you pick the bandwidth too small and too large, you start to get these outlying hills. Okay, and I literally picked the bandwidth here when up to the point. So where could I be wrong with this? There could actually be outlying hills that I have chopped off. So. I was the Chinese bulldozer, and created the new high-speed railway through. Oh, exactly. That's pretty much what I did. Okay, so this is now. Let's move on. So I actually, to be honest with you, I teach not this stuff, but kernel density, and I always, I teach cross-validation, all these methods. I don't believe in any of them, and I actually think, but that's debatable. I had like heated exchanges at seminars when I said this. I'm not sure how well this works with this crowd here, but I think as economists, we ought to have an idea about the object that we consider. Like outlying areas here, when these are elasticities, are really, really hard to motivate economically. Like if you could say, okay, these are two populations, but then come up with a plausible economic story for why there would be another mountain up here and nothing in between, right?
So you could say that instead of saying that you pick a parameter that makes things look good, you could say that you're imposing some sort of monotonicity.
Yes.
Or a unimodal.
Well,
You're basically saying it's a unimodal distribution.
Exactly.
Yeah,
exactly. Yeah. Well, what I always tell my students is that they should run cross-validation, and then they should say, after running cross-validation, I've selected a tuning constant, because that's actually what people write in papers, and that's just right. I've done cross-validation, and then I selected the tuning constant. Okay. So these are three experiments: a 2-cent price change, a 5-cent price change, a 9-cent price change, and you see, fortunately, the thing this is compensating variation, not cross-validation, okay? This is our welfare effect measure, and these are dollars a year, okay? And you see, if the price change is moderate, then we get moderate welfare effects, and if the price change is larger, we get larger welfare effects. So that's the first, nice, it works, okay? And let's look at a larger one. This is the 10-cent, like a little more than 5, more like 6% price increase. in gasoline. And what do we learn here? Well, there's a whole part of the population who is like almost not affected here, has, you know, welfare effects between 0 and $50. Okay, and then, but we also see we have a huge tail. Okay, and again, this is after controlling for things like living on the countryside, and I guess if you have several household members, you also have to drive more because there are more people. And yeah, I mean, if you ever lived in the suburbs and like I do and drove your kids around, anyway. So makes a lot. But even taking that out, there's a lot of heterogeneity in this effect. Okay, so in particular, there's a good chunk of the population between 150 and $300. Okay, and that's the heterogeneity that we care. Like if you're a policymaker, there's an average effect that you could care about, but you know these are the people who will vote Tea Party here. Okay, you're cutting into my freedom, you know, you bloody communists. Okay, so I'm paraphrasing there. Okay, so the interesting thing here, and this is, or can I just, okay. Mm-hmm.
Why is this
Never below? Oh, because by definition, the compensating variation is by definition positive. Like you didn't see that with the formula, but actually the formula is such that it can only be positive.
So is there an so you're saying like 150 is like.
Yeah, well, I mean, this is, I should say, this is something like the gross welfare effect. I mean, what this analysis doesn't take into account is that the government is going to be richer with the money that it levies on, you know, the consumer, and then will provide some other stuff with it. So there will be, like, for instance, they could just give it to you as a tax break, right? And then, you know, the total effect is, you know, is less clear. This is like the gross effect, and by construction in this formula, the gross effect is actually not true. If gasoline was a given good, then actually the compensating variation could be negative. So this actually also says, but that's a very exceptional economic situation. That's a situation in where if a price increases, you're increasing the consumption of that, and that is because, let me get the story straight, because you get poorer, and even though the things get more expensive and therefore less attractive, you actually get so much poorer that you have to discard the expensive stuff like caviar, okay, and you're going into potatoes, okay. But for gasoline, I don't think that's the case. So this.
So but your previous chart shows people that.
I know.
Like that shows people.
Yeah, there are some people here.
So wouldn't they have a negative compensatory?
But we'd have to look into the formula. Maybe not even that. I don't know.
What's the meaning of the CV? This is basically you're looking at how much money they spend under the, like, is it comparing two counterfactuals? How much money you spend under the increase versus how much you spend without the increase?
Yes, exactly. So CV is really, I mean, if the theoretical definition was, you know, holding utility constant, this is important because the thing that you observe is not in utility units, it has prices and income, but holding utility constants, you have to work a little bit for that. But holding utility constant, it is the change in the expenditure, you know, if you go from the base price to P. In our case, this is 131 and this is 140. Okay, so this is the guy, and I know by theory that in the special case of you know, the linear model that we're studying here, it has this form. I actually, I mean, looking at the formula, it's actually a very good point. I don't see why that guy should be positive always if the betas are negative.
And you're also plugging in the overall mean gasoline price, because isn't there variation in the prices between?
Yeah, so what I did here is actually, I did it for every price, for every, income. Actually, price, it doesn't matter because price is deterministically varied. So what I do here is, and the random coefficients are independently distributed of price, okay? So for, yeah. So price is just like it, but actually here's income.
Wait, is P0?
Yeah, this is P0 and delta P is but P0 is 131 and delta P is, you know, 140 minus 131. 0.09. Don't ask me why I picked these numbers. Okay. Now the thing is here, this actually depends on W too. So what I did here is I computed it for various values of W and then integrated out W with the density of W. Okay. But it's true actually. I mean, from this formula, I don't see why that should be positive, given that some of the I have to investigate. Good point. Yes. So you're not holding income constant. So in consumer demand, there is this distinction between holding, utility, being like on a fixed utility level and being on a fixed income level. Okay. So what economic theory in some sense only works on the utility level. And I mean that in the sense that, for instance, because of that given good phenomenon, in the world of prices and income, there could be something like given goods, But if I hold utility constant, then actually the price derivative of the demand function with respect to utility, holding utility constant, and this is actually called the Higgsian demands, that price derivative by economic theory has a certain sign. Whereas the price derivative of the thing that I can observe, which in our notation is P of X, P and W, prices and income, that doesn't have to have a sign. But there is a relationship between the Higgsian demands, and these are called the Marshallian demands. So the observable guy and the theoretical guy, they differ somewhat. And you probably have seen that picture with a what happens if you substitution and so on. So this is the substitution effect is always like being on the same, like usually you have a price change like that, and we decompose that into a pure holding utility constant effect. And an income effect. And that's also the way how you can go from one to the other. But you're right, I mean, this is actually on the level of Marshallian demands. They could be negative, but I'm still kind of surprised from the formula that, I mean, there's not a lot of mass here, okay, just to be clear. I mean, the thing kind of ends here, and 90-odd% of the mass is in the right area, okay, but there's some mass. Maybe I actually just didn't compute it, because the way that you compute it is point-wise, and maybe I should have done that in the negative. Okay, very good point. Thanks for spotting that. But the main message wouldn't really change, okay? I mean, this thing, at best, it's going to have a little bit of a tail here. This is not going to get a second. I mean, given how few people there are, negative overall.
So just so I understand, so this is basically saying if you increase the price by 9 cents, this is
yearly dollars, what your change in the cost function would be. Okay, so this is for a cent change of $9. The vast part of the population has a change in the utility compensated expenditure function. The cost function has costs of between 0 and $50 a year. Okay, which is a very sensible. I mean, I like the results actually a lot, given how complicated and all these things. I mean, I think they're very sensible. But I agree, I should have done that.
Just to state, in principle, what someone would demand to be compensated for the increase.
Exactly. So if I was the government, and if I knew that if I knew your coefficients, and I knew in the end you would be here, then to make you happy and not go on the barricades, I would have to give you 200, and if you were here,
I'm actually over here.
Over here? Oh, this is just driving. This is not flying with your private jet or something. Just a quick remark. This is kind of a personal thing here. That's interesting because that picture, I should probably wrap up, right? But that other picture is actually from an alternative way of modeling heterogeneity, which is actually closer to what quantile treatment effects are. So if you were to go something like Alberto's work with some hand waving, non-sepal models, then in the same framework with similar assumptions, you actually get similar independence assumptions, but less random coefficients and instead more non-parametric elements in the structural function, you actually get this result, which kind of is qualitatively similar, but a little bit larger. Anyway, so this is just, I mean, just illustrating that the specification in terms of unobservables matters for the results. Yes?
So how precisely is this estimated out of your procedure?
Standard errors could be obtained from the variance formula, but I didn't do it. I actually did bootstrap it. I don't know why I didn't.
Oh, okay.
I didn't plot the
Because
picture.
I'm thinking again, you may be.
So you would get like a, you know, a kind of a sausage around the graph.
So you may, I'm still thinking you may be able to do better by just assuming a normality and then
Oh, absolutely. I mean, this is going to be imprecisely estimated, but you also see that the thing. I mean, it's certainly not normal.
Right.
Okay, so that would be a bad assumption. It may be log normal,
yeah, but
but
this is actually like transformation from your model. Right?
that's right.
So
Yeah.
it's kind of
Yeah. So the question is, what happens if you assume normality here? That's another interesting question that I could actually do.
Right.
Okay. Why don't I wrap up here and leave the rest for discussion or whatever. Just as a short notice, a short you know, remark or footnote, there's a way actually using some of Hido's work as a building block to combine that. And essentially what you would do there is, instead of just conditioning on the observables, as we discussed, you would also condition on something which is called a control function, which is something that you could get from a first stage regression of the endogenous regressor. And then the same logic would apply. You would do everything conditionally. Okay, why don't I leave it here?
Thank you very much. We have a few minutes for Q&A. There's a fancy new microphone to record your questions for posterity. So if you have one, you can pass it around. Anyone wants to come? Get their questions out. I brought the microphone out. Now no one wants to come.
Oh, you.
Can you talk for like 2 minutes about the endogeneity correction of the instruments? Have you applied this there or how?
Actually did apply it there and actually didn't matter too much, funny enough. But this is, so I can tell you a little bit what I'm doing then, and then you'll see the relationship. So what I'm currently doing, and there's actually going to be a demand meets econometrics meets IO conference at DC in December. So for those of you who are interested in this, we have all, like whoever is, you know, big and relevant in that literature, without any bragging, okay? Or maybe a little bit. So, so this is not what I did up to now, but this is what I'm going to present. So this would be such an IV equation, and your identifying assumption would then be that Z is fully independent of all the random coefficients. So that's a model that I've been now working for the better part of the last 5 years. So what I did actually is, if instead of A1Z, there's a function M of Z without heterogeneity. Okay, so this is what I did. In which case, A0 would be exactly this control function thing that I would have to recover from the first stage, which I can do with just the residuals here, okay? And then conditioning on A0, the whole analysis would be just by adding a kernel that localizes in A0. I mean, just doing everything conditional on A0. But what I'm currently working at is allowing also for a richer heterogeneity structure in the selection equation, or in the IV equation. And then another thing that I'm working at is modeling it jointly with car demands. Because in the short run, you're the government, you're increasing gasoline by what, you know, let's suppose this is substantive, okay, you're increasing it by 30%. Then people will substitute to you know, cars with a lower mileage. And I used here a variable called SUV, okay? So that's had nothing to do with the unit sphere, okay? That actually means literally SUV. So one model could be gasoline demand or gasoline consumption is a function of prices, income, okay, and whether or not you have an SUV. And then whether or not you have an SUV depends, amongst other things, on the expected gasoline costs, okay? And that would be a model to model the simultaneity of both decisions. So in the short run, you would have this effect, but in the long run, the effect would be smaller because people would substitute away from SUVs. I mean, that would be my guess anyway. I have public transportation. That's one of the control variables I'm using.
So back to this, right? The reason why I thought it would be less than zero is because gas gets so expensive, people just give up their cars.
Yeah, but again, that's something that you then really would have to model in such a framework, because then you also have to make a statement about what the effects of having or not having a car is and so on. But you're right. I mean, eventually, if gas becomes very expensive, we're all gonna bicycle to work. Probably would be better anyway. Okay, well, thank you so much. Yeah.
Great talk. Really enjoyed it. That was a lot of fun.
You like it? All right, let me just turn this one off.
Yeah, definitely. You should be muted now.
Yeah? Okay. Hi, ja,
Alles gut zu sehen, ja.
Ja.
Lass mich mal ein bisschen noch was zu essen. Ja klar, mach das mal. Ich muss leider zum Teachen laufen, aber.
Ja, absolut. Ja.